The first one that I'm going to show you is our development reactor, the so-called Supercritical Reactor 1. This is a reactor that is fairly accessible, so where we can very easily access any component. So we can try different synthesis routes, we can try different materials, and we are not concerned with clogging the reactor or with doing anything wrong, because we can very easily just disassemble it, clean it, and reassemble it. So it's a perfect reactor for development purposes. Here, we usually run with fairly low flows of precursors because the tubing is fairly small. So all of the tubing in the reactor is actually a standard 1/4 inch wedge lock. So if we want to have a good residence time during the reaction, so to have all the reaction happening, we cannot flow with gigantic flows. So we usually keep the precursor flow to 5 to 10 milliliters per minute. So this is suitable for small synthesis, usually around 1 gram, maybe 2 grams. But if it's more than that, it starts to get a really long synthesis process here. Then we have a slightly more automated and user-friendly reactor, which is our Supercritical Reactor 2. It's already thought in a slightly more upscalable version, but from a construction point of view, it's actually very similar to the Supercritical one. So it's still fairly small amounts, but a little bit more towards the production side. And then what we have here is actually our more large-scale reactor, the so-called Supercritical Reactor 3. And it consists of different sections. In this first section here, we have the different containers for the precursor solutions and the solvent. Then in the second section here, we have all the pumps and the controls for the valves that are mixing the precursor solutions and the solvents. Then here in this part where you cannot really see anything, there's the actual reactor, which looks more or less like the other ones that you already saw. So it's basically some tubes and where the precursor are mixed. And then in the last part there, we have the tapping section, where we can either tap small amounts of material or up to 100 liters of product. So this is meant to be also used for really large upscaling of this flow production. And then everything is controlled with this graphical interface here. So we can control the pump speeds, we can control the temperatures, we can control the pressures, we can control the different flows, and everything is plotted. So after the experiments, we can always extract all the data throughout the whole synthesis, so we can correlate the conditions during the synthesis with how the products also turned out to be. So this is it for the production part for now, and I will show you a little bit of our testing setup here. Here we have our electrochemistry testing bench, where we have 4 independent RDE setups that are controlled with one potentiostat down here. The 4 channels can actually be run independently from each other and in parallel. So, and each one of them has their own gas supply. So ideally, we can set up one measurement, set the gas supply, we control the rotation speed and everything with the potentiostat. Then we can get the first measurement started, we can set up the next one, get it also started and running in parallel. And so we can have up to 4 measurements running at the same time, which greatly improves our time efficiency, especially now that we have 38 synthesis products to characterize together. And then I will lead you to the other room. Here we have our viscosimeter. It's not really used super much in this project, but it's always good to have when optimizing inks and slurries and stuff like this. Here we have our filtration system, which we use when we want to try to clean the products with filtration, which we saw was not really ideal for the latest synthesis. Then here we have 2 development batch reactors. Each of them is 3 liters, so they're a little bit more capiant than a standard oil bath solution. If at some point we decide that we want to upscale the batch synthesis, we can also, of course, do it here. And once we optimize the conditions here, we can move to some bigger reactors we have that are 40 and 80 liters. But I will not show them to you now because we have a little bit of a mess in the other lab. So I'm going to keep it with the small reactors here. And then finally, if you follow me to the last room, here is where particle size determination. The first instrument here, where you can see this beautiful blue solution, we have ATO inside right now, is our laser diffraction instrument, where we can measure both powders or suspensions or any combination of the two. And it's very accurate in the hundreds of nanometer range up to the millimeter range. And if we realize that what we have is very small, then we move to our DLS tool here, where we can measure very accurately down to the nanometer size and also run both zeta potential measurements and assess the dependence of the zeta potential on the pH.
Yes, this is one of our spray deposition robot. So we have a semi-automated system for doing spray deposition. So we have a hot plate with a vacuum suction, and then we have a sonic spray head, and we have different prompts for camera system for visualizing, and there's also setting a laser in the back, so we can do automated process where you run this deposit a layer, and then you can photograph and look for defects. We can also scan with a laser to see if we have more or less the same thickness or height. And we've used this for producing a lot of electrodes for fuel cells. So this worked quite nice. We have also a second system that is an optimized system compared to the first one. So it's quite similar with a heated vacuum plate. The difference is that here the vacuum plate is fixed, and then the spray head can move in 3 axes. And the advantage here is that this is actually also optimized to get the right airflow through the reactor or through the deposition to control it. So that the problem with the first one is that when you have the substrate plate moving back and forth, it's difficult to control the airflow over the reactor or the electrode deposition robot. But in this one, because it's fixed, we have a controlled laminar airflow going through. So this one we haven't tested on that much, but it should be able to give even more uniform electrodes. So from this we can basically make any size up to 40 by 40 centimeter electrodes.